because of the advantages that I have told you in the previous slide. All right. So what happened in the last 20 years is that why this stem, or why this aberration correction has become so much popular these days is because okay, even before that, I just want to tell one thing, that aberration, what does it do is that a point object, just like all these electron lenses are magnetic lenses, so they have aberrations. So if you look at a straight wall through a glass of water, you would see that the wall looks like a bent object. The straight wall looks like bent, so that's an aberration. All right, the similar thing happens here. So a point object acts like a disk. So the concept that aberration can be corrected in theory was present from 1950s. Serzer and people like them has actually predicted that, okay, if we use a series of octapole and hexapole lenses in combination, then we can get rid of aberration, and then we can make actually an electron beam or electron probe less than an angstrom, and we can see really nice features at atomic scale. But the problem was that to pass information between these series of lenses, you need very high computing power, which was not available, at least commercially, until late 90s. And since then, people tried to correct the aberrations, and the first aberration corrected stem actually became operational in 2009, and it was at LBNL, and subsequently they brought another aberration corrected stem. So for the first stem the resolution was 1 angstrom, and for the second stem the resolution was about 0.5. So the microscopes are known as Team 1 and Team 2 and Team 05 actually. So I was fortunate enough to use both of those microscopes when I was a postdoc. So it was a nice experience. So once we have an aberration corrected beam, so our beam is very small, then we can see these kind of images, and you can see actually a single layer atoms in a nanoparticle. In case of a nanostar, from where this nanostar, the branching started, we can pinpoint up to the origin up to a single atomic layer. Then there are many more applications, such as this precipitation hardening in aluminum alloy, where adding zirconium or scandium actually strengthens the alloy by producing this kind of inhomogeneous precipitates, which stops the crack propagation, dislocation propagation, so on and so forth. But people are interested to know the phase of these precipitates and how the surface actually look like between matrix and these precipitates. So you need STEM to really see all those fine details. And here is an example of a optoelectronic experiment where there was a 7-fold increase in optoelectric Kerr effect, and then some people said Carr effect, Kerr effect, whichever it is. So here we have seen that there is a elongation along one set of atomic layers at the surface, and we subsequently explained this phenomena of 7-fold increase in Carr effect using STEM images and spectroscopy later on. So we can determine new phases using STEM, and as it is evident. So it is an example of a aluminum scandium alloy. and you can see and it is projected along 001 direction of a cubic unit cell, and you can see that the corner atoms are occupied by scandium atoms, and the face and the center atoms are occupied by aluminum atoms. So just by imaging, as I said, the image is a Z contrast image. So if there are two kinds of atoms present in your sample, you can actually directly interpret it. But I would show you later that we are using this. We have taken spectroscopy from this area to further prove our case. All right. So last thing on the Z contrast stem is that so this is an example of a few atoms of nickel were deposited. Less than 0.5% of nickel was deposited in carbon fiber, and we have actually deciphered that, okay, where those atoms are. And because again the stem is that the carbon doesn't scatter much, so that it has a hazy background, and nickel scatters much more in head of stem, so we can see them just by looking at the contrast. All right, now once we have a stem probe, which is very small, we can what happens is that these incident electrons pass through one atom precise, we know from where that X-ray has come. All right, so we can collect that X-ray using X-ray detectors, and the modern X-ray detectors has 4 or 16, 16 even 16 valves to count those electrons. So X-rays, sorry. And we can get very high quality map within few minutes, which was even 10 years ago. To get a quality map, X-ray map, we used to have, say, wait for 30 minutes or 40 minutes, and by that time your sample would move, and things were very messy, so to say. But nowadays we can have very nice detectors where we can collect X-rays, and then from the same time we can get crystal structure information from the same area. And here is that example again. So as I said, we can do atomic resolution X-ray mapping. And as I said before, that at the corner there are scandium atoms, and at the center and the face there are aluminum atoms. So we did X-ray mapping from this area, and I have shown that okay, that is indeed the case. There are aluminum atoms at the corners. And scandium atoms at the corners, and aluminum atom at the center. Okay, and this work was published in Microscopy Microanalysis in 2019, and so that's one thing. And the second thing is electron energy loss spectroscopy. So the incident electron that interacts with the sample and produces an X-ray, in that process it loses some of its energy, and based on their energy loss, we can disperse those electrons below the imaging camera actually. And what we can get is a spectra which is known as electron energy loss spectra, and we can actually use those electrons to form a map, just like I did with the X-ray map as well. So the good thing about it, this EELS, or electron energy loss spectroscopy, is that the energy resolution is about 1 eV, and typically 1 eV or below. And actually, if the electron transition is happening from subcells of an atom, we can actually determine that. So if there is any distortion in your crystal, and if there is any say change in oxygen environment in your oxide, so on and so forth, which changes the electronic structure of your sample, we can actually see it from the yield spectroscopy. All right. So here is a comparison between STEM and yields. So EDS has a better signal to noise ratio, so we can get very high quality maps in minutes, and in yields that's a problem. We can look into thicker samples in EDS, but we cannot do that with yields. For yields, we have to have the upper limit is about 20 nanometers. Upper limit of thickness is about 20 nanometers. And yields requires a spectrometer alignment, which is not so easy. But EDS doesn't require all those things. The disadvantage of EDS is that it cannot detect elements very precisely below oxygen quantitatively, and the energy resolution is very poor compared to yields. So as I mentioned, yields has a energy resolution of about 1 eV, where the energy resolution in EDS is about 100 eV or so. So the bonding information cannot be obtained from EDS. But if you have STEM, EDS, and yields, you can have complementary information about your sample from all these three techniques. So, and then we can do, of course, simulation and simulation of diffraction patterns, simulation of STEM images, and other such things. We have capabilities here, but that's not so important at this point, so I would just skip this part. And we can run our instrument at 80 keV also. So if you want to see virus and all those things, carbon nanotubes, which are very beam sensitive, you can actually do that. All right. So, so for last 10 minutes, I would use, I would talk about how I use these things for making stable lithium-ion batteries at high voltage. So as you know, the 2019 Nobel Prize in chemistry was given to 3 persons. So one of them is Stanley Whittingham. So he is standing here, and during my postdoc, my funding was from his group. So we used to meet in his twice a year. We used to meet in his lab and discuss projects and so on and so forth. All right. So the aim of his research during that time, that means from 2016 to 2018, in those two to 3 years actually, was to make the batteries more stable at high voltages. So why it is so? So lithium-ion batteries work in an intercalation geometry. So here is a very it's a caricature of lithium-ion battery. So the cathode is on atomic scale. So the blue part is actually the nickel atoms, and then there is lithium ions, and there is a layering between nickel ions, lithium ions, nickel ions, and lithium ions, and that's why it's known as a layered structure. And so that's cathode, and in between cathode and anode there is electrolyte, and when you charge the battery, these lithium ions actually go and stack in the anode. And then when you discharge them back, they come back and go to their respective positions. So what happens in regular batteries is that we use it at 3.6 to 3.8 volts, so that only about 50 to 60% of lithium is actually taken out from these batteries. So we are not using 40 to 50% of the efficiency of the battery, because we cannot extract more lithium than that. So why we cannot do that? Because if we take almost say 80 or 90% lithium out from the sample, then this cathode structure starts to crumble. Not only crystallographically, what happens is that at high voltages, when lithium is out, the electrolyte starts reacting with nickel ions, and they form all sorts of densified phases. So what happens is that in this cathode, nickel has a valence of +3, and when at high voltage electrolyte starts reacting with the nickel, it reduces its valence to +2, and then they occupy the lithium positions. So that happens during charging. Now, once you discharge the cathode, once you discharge the battery, when lithium comes or tries to come back to the cathode side, what happens that their positions are occupied by nickel ions, and that's what is known as densified phases. And this increases the impedance of the battery, and these reactions is accompanied by oxygen loss. So your battery swells up, and if there is any hole or piercing, then it can lead to catastrophic destruction, and so on and so forth. So what we tried to do is that we deliberately kept these batteries at 4.75 volt, from where we can at which voltage we can take actually 90% of the lithium out of the battery, and we kept it at charge condition for 2 weeks, prolonged charging, and then finally we discharged, and we saw that okay, approximately 60 to 70% of the lithium is going back to the cathode. They are not going back to their respective original positions, but they are still going back to the cathode. And then we tried to find out, okay, what is happening at very, very atomic scale. This is an atomic scale phenomena. So we had to do STEM and yields from the same area of the sample. And so why so? Because by using STEM, we can see the atomic scale structure at the surface, and from yields from the same position we can see if there is any oxygen loss, if there is any valence change in nickel, and so on and so forth. All right. Here are some experimental details. So one of the things is that to get this transition, okay, so there is a surface phase transformation occurring at the surface from original layer to a rock salt like phase, and via a spinel phase transformation. So to see this transformation, you have to orient these battery particles in a certain direction, in a certain zone axis. Only then you can see the movements of the atoms between the structures. All right. So this particular zone axis is 110 zone axis of the original layered structure, and we use that to get the diffraction pattern. And here is the projection, and then these are the atomic scale STEM images from those surface areas. All right. So one thing we did is that we used yields on standards to determine the valence. If you want to know more about this technique, you can ask me in the Q&A section, and you can see this paper as well, micron paper. It is by my boss, my supervisor. So it was an earlier work. All right. So we use standard to determine the valence of these materials. So what we found out that there are two types of phases occurring, surface phases occurring at the surface of this lithium-ion battery cathodes, and one is layered with lithium nickel moving into the lithium layer, but what is happening, we have quantified that approximately 25% of the nickel is actually moving from its original position to the lithium layer, but there is some vacancies and vacancies and dislocations and all other things, which actually is providing sites for lithium to intercalate into the layered structure. And then we have found an extended phase, which is rock salt like phase, which people which people termed as a rock salt, which is crystallographically a rock salt phase, but we have determined from the valence that it is more like a spinel structure. So this was a unique finding, and later on we collaborated with our theory groups to determine the exact nature of these phases. That work is still going on actually. All right, we determined the extent of the surface phase transformation at high voltage. So how far these surface phases propagate into the battery cathode. And we have seen that it in case of layered light structure, it goes up to it stops at around 10 nanometers, but in case of this rock salt like phase, it goes beyond 20 nanometers. So, and we would determine the same thing using quantitative yields as well. So I'm skipping this part. Yeah, if you have any questions, you can ask me later in the Q&A section. Basically, from these last two slides, what we have determined is what we have determined is that there are two types of structures forming at very high voltage in lithium nickel oxide cathodes, and they have distinct crystallographic structure from the bulk, and we have determined it by using high resolution STEM and yields. All right, and this work was published in Chemistry of Materials in 2018. And the second part of this work is actually still going on, and it will be published soon. All right, so that's about my talk, and then we can do 4D tomography using our machine. And if you want to see 3D information about our sample, about your sample, you can see that. And we can do EDS mapping in 3D scale as well. So that's why we are calling it a 4D tomography. So that's one thing. And we have a liquid cell TM holder where we can see samples in their liquid environment, and we can actually form a pseudo cell inside a TEM, and we can see when we are charging or discharging, and then how the cathode side reacts, if there is any bulging, and so on and so forth. Here in this technique, the resolution is maximum at nanoscale, not atomic scale. All right, and we can do, of course, we can do heating, we can do nano indentation, and see, we can measure a force curve, and we can, of course, do electrical biasing, all these when we are seeing the sample. So it's a work in progress, and that's all about our capabilities, and that's all about my talk today. Okay, thank you.
Okay. Thank you, Dr. Pinaki Mukherjee, for this nice talk. Now the forum is open for discussion. Any question? Please unmute yourself and ask question to Professor Dr. Mukherjee, please. Any question?
Hello. Good morning, sir.
Hello.
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 Yeah. Go ahead and ask.
Hello. Good morning, sir. Sir, only one question, sir. Sir, in TAM, use a magnetic lenses. Sir, magnetic lens mein how to change focus length?
Focal length, you just change it by the objective lens current. So whenever you change, these are electromagnetic lenses, all right. So if you change the current in your, whenever you change the knob, say objective or focus knob in your TEM, it actually changes the
Yeah.
current in the solenoid, and that way you can change the focal length.
Okay, sir. Thank you so much, sir.
Mhm.
Dr. Mukherjee, I have one query.
Mhm.
Generally, from EDS, we can know the composition of the material, how much percentage each element is there in the in any material, right?
Mhm.
So, what is the resolution for that? Means generally, we get a lot of reviewers comment that EDS will not tell you that exactly 15%, 14%, or so. What is the resolution, and what factor decides the resolution of any composition which is present in any material?
Okay, so
Hope I am making my question clear, right?
no, your question is very clear, but the answer is
Okay,
not one sentence answer actually. So
okay.
there are 2 or 3 factors that determine the exactness of your quantitative analysis. First thing is, okay, there is an absorption factor. So the morphology of the sample. Say if your sample has a tilt, and say one part of the sample is actually blocking one set of detectors, then there would be problem. Your signal would be low along that direction. Okay, so that something you have to take care of. And the second thing is um, uh, how to say it. Uh, say two elements. Say in your sample you have 2 elements, say nickel and copper. Say
Okay.
uh, so their peaks are actually very close to one another, all right. So you have to use a very nice deconvolution so that you can very precisely separate those peaks. So if you are not careful enough, then what would happen is that you'd get wrong information about your sample. The third thing is there is always a correction factor associated. Say I am working on, say, nickel oxides, all right. There can be different types of nickel oxides, all right. So if you have a standard sample, say NiO, and then you put that nanoparticle NIOs into your sample, into your TM, and you get a nice spectra. And based on that, you see that instead of being 50-50, it is a 65-35. So you get a correction factor out of that. You can use that. And the fourth thing is below mm, below oxygen. If you try to measure those elements quantitatively, it's better to do yields rather than EDS.
Low atomic number elements. Yeah.
Yeah.
Okay. So let us thank the first speaker, Dr. Pinaki Mukherjee, for giving us a very nice state-of-art STM facility, and let us thank him once again. Thank you very much for this informative talk.
Thank you.
So let us move to the second talk. The second talk is by Professor L.P. Purohit. He is currently head of Department of Physics and Dean Faculty of Science at Gurukul Kangri University, Haridwar. He supervised nearly 14 students for research work leading to PhD degree. He published more than 100 research articles in various international journals. He delivered nearly 14 invited lectures in various national and international conferences. He is members of various board of studies and research degree committee in many Indian universities. He is also a reviewer in various reputed journals, and his research interest is basically compound semiconductors and metal oxide nanocomposites for electronic gas and humidity sensors, photodetectors, photocatalysis, and many more. Today, Professor Purohit is going to talk about metal oxide nanocomposites, the functional materials. So let us invite him for delivering his talk. Professor Purohit, kindly give your lecture. and enlightened us.
Thank you very much. Do you hear me? Am I audible?
Yeah, yes, sir.
Yeah. A very good morning to one and all. First of all, I would like to thank the organizers for inviting me to deliver a talk in this international conference, e-conference on recent advances in physics promised to society. And I congratulate them that they have nicely organized the one-day session. And in the present COVID pandemic, this topic is very relevant for the physicists. So I, thanks to Professor H. Chandola, convener and HOD, Department of Physics, and Dr. Ashish Adarsh Chaudhary for doing this very good job. Actually, is it visible?
Yeah, your slides are visible to us. Yeah.
Yeah. So I will be discussing on metal oxide nanocomposites, the functional materials. As we know that nanotechnology is an emerging field that covers a wide range of technologies which are presently under development at nanoscale level, and the behavior of nanomaterials at nanoscale level is much different as compared to their bulk counterparts, and which is due to the size confinement, dominance of interfacial phenomena, and quantum effects. So what are the functional materials? Why we call them functional materials? Actually, these are the fast growing materials, advanced materials, and composites having the properties like shape, their electrical conductivity, their mechanical properties, which are responsible to external stimulation. It may be a thermal stimulation or electrical or mechanical or optical, basically. For example, we have piezoelectric materials, we have energy storage materials, we have sensors, and actuators, we have photocatalysts. So these are some functional materials which are used nowadays. Second thing is composites. Composites are the combinations of two materials in which one is called reinforcing phase and other is the matrix phase. Normally, the reinforcing materials are strong and like fibers and seeds and other particles, while the matrix materials are always ductile, or they are tough materials. And we know the natural composite are the wood, the bamboo, and the bricks, which are well known to us. Now, what is nanocomposite? So it is a combination of a matrix in which different materials are combined to have a new property, and those properties are different from the individual material, with the condition that they have the size one of the material has size in the range from 1 to 100 nanometer, that we call the nanoscale range. And as we know, that nanomaterials have gained a lot of interest due to their very high, important, improved properties. Basically, scientists are being attracted for metal oxide nanocomposites and their technological applications in optoelectronic devices, sensors, energy sources, photovoltaics, etc. And actually, the main factor is the size reduction at nano level, and that size reduction is different property, giving property, then its crystalline form, and the material acts like a isolated atom or molecule. So this is the main way it behaves, like a isolated single atom or molecule. So the quantum confinements are there. Normally, we have semiconducting materials, and they have the advantage of generating the large number of carriers, which is required for the stimulation, and they are also useful for the environmental remediation, which is the need of the present day in this COVID pandemic, that we need the material to delete the environment.
Professor Purohit, sorry to interrupt you. So I request you to kindly make your PPT in full screen so that it is visible to all of us. Huh?
Okay.
Yeah.
Now it is visible? Yeah.
Yeah, now it is fine. It is okay now. Yeah.
So,
Professor,
yeah. Actually, I am not very used to.
you may do one thing.
Yeah.
No problem, sir.
First, stop your presentation, and after that restart again. Present now,
Okay.
so that it.
Present now. Yes. And screen is there. Now it's fine.
No.
Your slides are not visible to us. Now it is visible. Yeah.
Yes, sir. Yes.
It's visible. It's visible now.
Yeah. Make it full screen, sir.
Yes.
Yeah.
Okay, sir.
So we are interested for the metal oxide nanocomposites for their functional applications, and I have selected two applications. One is the gas sensing, and other is the photocatalysts. These are the important issues. Actually, in case of gas sensors, I have taken the composites of zinc oxide and cadmium oxide. And in case of photocatalysts, I have chosen the ternary composite of zinc oxide, TiO2, and CDO, basically. So let us have some idea of sensor. What is a sensor? We all know that sensor is a device which senses a signal and which converts it one form to another, rather in electrical form, finally. And they are normally the electrical or electronic. And they have a lot of applications in automobiles, machines, robotics, and all that. The gas sensor is a subclass of chemical sensors. We also call it as a chemiresistor. And in fact, it measures the concentration of gas. It interacts with the gas, and the sensing depends on the breakdown voltage of the gas because it is ionized by the application of the voltage, and by measuring the voltage and current discharge, we can get the concentration of the gas. Basically, this is the main physics behind this. We have different kind of sensors, thermometers, thermocouples, and all sorts of these sensors, and which are used for different applications, including the process control, environment, fire detection, home safety, and all that. Major issue of the with the sensor is the operating temperature, and humidity is also the parameter. So we need to care of these two things very clearly. Now we have different kind of gas sensors like metal oxide based, capacitance based, acoustic based, caloric conductivity based, and optical gas sensors and electrochemical also. But I will mainly discuss on the oxide based. Is it audible?
Yeah, it is audible.
Yeah. So these are different kind of sensors depending on the type of applications we require. And basically, we will talk about the metal oxide based gas sensors, which we generally known as chemiresistors, because their resistance changes when the gas molecules are adsorbed by this. And this is nothing but gas solid interaction, which causes the change in resistance. Basically, there are three things. It is adsorption reaction, which is nothing but the scattering of an electron. There is a reduction of oxygen ion, and there is a change in the resistivity or conductivity. So these three things are there in case of resistive gas sensor, which we have used here. And we can develop the gas sensors by making it a transducer with some signal conditioning and all that. Now, because gas sensing and human nose and human eye is our best sensor. We call it electronic nose and electronic eye. And this sensor is nothing but the artificial nose. As we know that the typical human nose has 400 type of scent receptors to smell about 1 trillion different odors. But still, many of us do not have the capacity to identify and type or the concentration of the gas in the atmosphere. And this is where the sensors are in the picture. So they are active enough to respond the gases by using the basic physical and chemical properties, behaviors. The main issues are parameters are the defects, lattice, grain size, and porosity is a very important factor. In addition to the thickness and the geometry and electrical contacts. So porosity is an important factor. As you see here, every sensor should be porous enough so that it can be well interacted with the gas molecules. So let us come to our actual work which we have carried out, and we have different kind of nanocomposites like CDS, ZNS, zinc oxide, MgO, and all these shown in the PPT. And we have selected here the cadmium oxide and zinc oxide and their combination. This is what, when we go from the bulk to nanomaterial, there is large increase in surface area, and this is the main reason. So let us come to our zinc oxide, which is very brilliant material, and it has a large band gap, 3.3 lepton volt, and as well as it has very high exciton binding energy, 60 MeV. That's why it is very useful for ultraviolet, and it is very transparent in the visible region because of its high band gap, and because of transparency can be used as a substitute of ITO. And we know zinc oxide normally N-type semiconductor, and it has a lot of defects, negative defects like oxygen vacancies and interstices, and it exists in three crystalline forms: rock salt, zinc blend, and quartzite. Another important metal oxide is cadmium oxide, which is uh, somewhat less transparent as compared to zinc oxide, and it also exists in two crystalline form, that is rock salt and cubic structure. Rather, and because of its lower band gap, it has 3.2. It is around 2.2 electron volt. It has a very better conductivity, high conductivity as compared to zinc oxide, though it is N-type semiconductor. So that's why it plays an important role because of its conductivity and lower band gap, which is at par with the visible light. So this is what we managed to have the band gap engineering. And when we mix them, so that we have a nanocomposite. And as I already told you, that nanocomposites are very important materials. Their properties are being changed, and we have different matrices for this: ceramic matrix, metal matrix, polymer matrix. But here we will take the metal matrix nanocomposites. These are the structures, multi-layer nanostructures, and these are the applications. As usual, we have various applications in solar cell, LED, in piezoelectric devices, in TFT also, gas sensor, in photocatalytics, all that. So now our objective is to synthesize the CDO zinc oxide and to investigate different properties, maybe electrical, optical, gas sensing, for suitability of our gas sensing purposes. Actually, I am delivering this lecture for the sake of our new researchers, young researchers. This is informative only because in the 30 minutes we cannot explain each and everything in detail. So this is just informative to all young faculty members as well as for the young scholars, so that they are motivated and they can plan their work in this direction also. We have different methods for preparation of nanocomposites, and out of these various methods, we have sol gel and sputtering method as well as precipitation method. And normally we have in our laboratory we have synthesized by these two, sol gel and DCRF sputtering methods. The main thing is, while on synthesizing materials, we should have some nanostructures like nanowires, nanotubes, nanorods, some micro nanospheres, nanoflowers like cauliflower type. So this is what we require, and that can be confirmed by our same micrographs or HR10. Actually, for the synthesis, we have a very economic and cheap technique, that is sol gel technique, which is very easy and low cost, and it has all sorts of beauty. where we need the precursor materials, some solvents, some stabilizers, and just we have a simple process of spinning and coating the material. And the beauty is we can have thin film of desired thickness depending on the cycles, as well as we can centrifuge it and we can dry it for getting the powder material. So, and we can anneal the synthesized material as per our requirement at higher temperature. So this is a flow chart, as usual flow chart for growing the different metal oxide nanocomposites and nanostructures. And we take the precursors of different materials, we stir them, we add some MEA, and we add some MEA and we stir it for certain temperature. Then we make the homogeneous solution and we coat it for different RPMs in a spin coater, and we get the desired thickness of the thin film, or we can centrifuge it. We can add some enamelers and centrifuge it and wash and dry it. And they are finally annealed to get the desired films. We can also use some physical methods, that is the sputtering methods. That can be a DC and RF sputtering, which is again a very important, though it is costly method. It needs a high sputtering unit. And these are some characterizing tools which we have utilized from different laboratories in IIT as well as in our lab. So I need not going to discuss them. We can use XRD, FTIR, ipsometry for characterizations. We can have same as just given by Professor Pinaki Mukherjee. We can use AFM, atomic force spectroscopy. We can use secondary ion spectroscopy for our different characterizations and for our different informations. We can also have the EDX or XPS for the qualitative and quantitative study of different samples. So these are all requirements to verify everything what we have prepared so far. And we can also use, in case of powders, differential colorimetric studies for any information like transition temperatures, melting temperatures, and all that, for which we can use DSC unit, which is available with us. And for optical studies, we can use the spectrophotometer for the transmittance and reflectance, etc. And finally, for the electrical characterizations, we have Kirle system, and for this is for the DC electrical properties, and for getting the AC electrical properties, we can have the LCR impedance meter. And for the gas sensing purposes, we have chamber with sample holder and we have just three things. Temperature, change the substrate, and then we have changed the solution of that is concentration of the precursor solution. And we have found the different measurements results. First, XRD is very important, and this is the XRD of different samples at different concentrations of CDO. It is only CDO at different annealing temperatures, and we have a very clear cubic phase CDO, and we can also calculate the crystallite size and other parameters from the XRD. Around 13 to 37 nanometer was the size according to CS formula, and we see here this is the X-ray diffraction with different substrate, and this is the X-ray diffraction with the different concentration. So we see there are changes in the diffraction pattern when we either change the annealing temperature, or when we change the substrate, and we change the doping concentration. And this is the SEM micrographs, and this is again in 3 different ways for annealing temperature variation for different substrates and for different concentrations. And we see here at around 550 degree annealing temperature, we have nano cauliflower type structure morphology was obtained, and we have again different morphologies with variations in different parameters, and this is what we were expecting from the same micrographs for our application purposes. Further, we have done the optical studies. Transmittance is plotted with wavelength for different 3 parameters, and it is clear that they are all varying with individual parameters and with different parameters. And we have estimated the band gap. As usual, it is around 2.2 to 2.42 with variation of temperature, as well as there are change in band gap with variation of substrate, and as well as varies with variation of the concentration. So these all studies were done to optimize a particular sample for the best sensing purposes. And electrical characterizations were made, and from these we have it is clear that sample 2 S2 is having a higher conductivity, and it has the majority light 0.2 m, and that's why we can optimize this. And finally, the gas sensing properties were estimated. We have done photo sensing in this case, light on and light off, and we have checked the sensor response in terms of current, and we have it is clear that it is around 99.6%, around 90% response is there, photo response is there, and the response time is also very fast. It is around 10 to 25 seconds. So this is what we got a very good response, sensing response, and this work was published in these journals, which papers were published. Next issue was with the composites. In this, we have mixed zinc oxide in CDO, and we have done the different gas sensing measurements. Now the procedure is same. We can use the solder techniques. Here now we have 2 precursors, 2 solvents, and then we mix them in a proper ratio, and we have made 4 or 5 samples, 6 samples of different ratios. And the same thing, I'm not going to repeat the things. We did X-ray diffraction, we did the XPX and SIMS results, we did the surface morphology by same, and finally aim is to get optimized sample. Here we have Z3 sample was optimized, which is the flake-like morphology. We also carried out the AFM and EDX studies, and optical studies were done as usual, and we have found the transmittance and optical band gap. Now we see here the band gap tuning is there. Uh, the band gap is decreased from 3.1 to 2.15. So this was a very good result on doping of cadmium oxide, cadmium into zinc oxide. The band gap was reduced. So that's why we could able it in the near this. And we have done the electrical properties for getting the electrical current sufficient to for sensing purposes. And here we did the oxygen sensing instead, because oxygen is very much required, and nowadays also it is very much required for the human beings and for the automobiles also. In ignition of automobiles, oxygen is required, so there's a sensor. Just like we are facing the problems nowadays, lungs due to lack of oxygen supply. Same thing happens with the automobiles. So that we need a sensor, oxygen sensor, which is always required there. In case of mines, we need to sense the oxygen under mines. So we have we have employed the life-saving gases, and this is the setup, the same setup for oxygen sensing. And here we have optimized the temperature also, because we are interested to get the sensing at lower temperature. At higher temperature there is report, but at lower temperature no composites have been reported. And of course we could able to reach up to around 32 degrees Celsius temperature. Though the response was not very much high, but it is there. We got the highest response at around 150 degrees Celsius for a particular composition. And of course, we see here we have a very good response time, 14 seconds at 150 degree operating temperature.
Professor Purohit.
And yeah, I'm getting late. Sorry.
Yeah, we are running out of time actually. Yeah, please go
So let me finish this issue of sensing, and we could able to have selectivity for different gases like oxygen, nitrogen. And one beauty of the material was that we could got the contrast, same material for getting two gases, nitrogen as well as oxygen. One has the upside and other has a downside. So this was the beauty of our material, and this was also published in different good journals. So this is what we also utilize the sputtering techniques. I'm not going to detail, but the young students should try for the physical methods for growing the thin films using the sputtering techniques, and same studies may be carried out for getting the sensing response with good with the lower operating temperature, high response, and very small response time. So this is what I can conclude the first part. I will require 5 more minutes more, please. Is it possible?
Yeah. Okay, sir. Okay, please.
Okay. Because I have to discuss the protocol also. So finally, we could able to design a nanocomposite, to synthesize a nanocomposite for getting the maximum selectivity and very good response for oxygen and nitrogen gas sensing with a particular annealing temperature. So this is what we achieved our objective. So this is the first part of the talk, and the second part is again very interesting for the present scenario. that which is the heterogeneous CDO, TiO2, and zinc oxide nanocomposites for water purification under visible light, basically. This is very important issue, and we have used material TiO2 in addition to these normally used materials, CDO and zinc oxide, and making a ternary. And the important issue was that we could able to get the property in visible light. This was not reported earlier for ternary composites. Otherwise, all the water purifiers uses the UV light, which is very costly, and unless it has a low light also. We can use a simple LED bulb or simple fluorescent tube and 60 watt, 100 watt for getting our sensitizer material, this material. And the basic purpose, basic theme is the same. We just have a semiconductor with valency band and conduction band. Whenever light falls, electron hole pairs are produced, holes in valency band, electron in conduction band, and they expose to the outer atmosphere, and they have two hydroxyl and this O2 superoxide ions radicals, and they combine with the pollutants, and finally we have the CO2 and S2. So this is the basic principle of the purification and the photocatalytics. So this is what we have here. We did the same type of catalysis except the AOP, that is advanced oxidation process we call it, that is known as the photocatalysis. And while purifying the water, because we have added dyes, MO and MB dyes, we have also reported the oxygen demand, BOD and COD, which is required for the pure water, for drinking water. So I'm not going to discuss much about this. I just show you the results we have. Problem was that only 4 to 5% of the light is in the UV region from sun, and that is the main problem. We want to use the material even in sunlight. We can use our material in visible portion, because this is a big portion. The important thing is again that we should have a very low adsorption, fast recombination, and easy agglomeration. These are three different things which are required, and our ternary semiconductor compound achieve these all objectives. Again, the problem with zinc oxide and TiO2 is of band gap, which are large band gap materials. But CDO nullifies this, and the band gap is reduced less than 3 electron volt. This is the same methods. Soldier method was employed for making the nanocomposites. Here we have used the powder basically. And we did the XRD. TiO2 has a problem because in amorphous phase we cannot have the photocatalytic properties. But anatize and ethyl phase is good for this purpose. So this is very important that we should get these two phases in our XRD, and this was confirmed. And again, we need to optimize a particular sample for our final photocatalysis purpose, and this is what we can have the different parameters. Yes, it is the same macrograph, and yeah, this figure is very important. It has the nano rod and nano flakes and clusters and aggregation of particles. So it's the most optimized sample. This one, CT03, for other applications. And we did also SRM studies also, and again we got in this here. we have aggregation of small spherical particles collected with the clusters of CDO, and usually as usual, we did the optical measurement, reflectance, and we got the optical band gap, and it was variable. We did also PL also, yeah. And
Sir,
this is the final AOP.
kindly conclude, sir. Please conclude, sir.
So this is what we got the AOP, and around 90% the degradation of the dyes with a radiation of light at up to 40 minutes time. This is before and this is after. This is clear, and we have repeated the cycle, and we are getting a very constant results. So this was very important, and this work was also published in Applied Surface Science with a very good note because of very good stability, very high degradation, and use and it was in the visible light. So this is what we can explain the diagram the same manner. We have reduction and acceleration process, and we have not calculated that COD and BOD values, and they were very much reduced at per requirement. So this is again a very important issue, that DOD and COD values were intact and reduced up to a particular level which is required for the drinking water, and repeated we have repeated the measurements for different cycles for different dyes, and we got the very good results after first, second, and third cycles, before and after AOP. We see before and after. There's a big. This is before and this is after. Before and after. So very reduced amount of this. So this is what I conclude, that we could able to synthesize a ternary nanocomposite for making water purification setup in the visible range, and which has the enhancement in AOP under visible light. So thank you very much for hearing me, and any questions?
Okay, thank you, Professor Purohit, for delivering this nice lecture. We don't have much time, but still we can take one question from the student side if they are having. Please, one question for Professor Purohit.
Sound is not clear.
Hello, sir.
Hello?
Yeah, I'm Dr. Meenakshi Rana.
Yeah,
Hello.
please, yes.
Yeah, am I audible? Yeah, sir. Your talk was very informative. I just want to ask that is there are a number of nanocomposite, but why you choose only CDO, nanocomposite for gas sensing application? Is there any specific criteria for choosing this type of nanocomposite for gas sensing application?
Yeah, it is based on the literature as well as on the morphological studies, because we need a particular morphology for the gas sensing purposes. So that's why we have selected the CDO and zinc oxide. And toxicity is very important also. So zinc oxide is very user friendly.
But according to me, I think CD is much more toxic. Cadmium is
CDO is somewhat toxic, but but zinc oxide is very good in that case, and TiO2 is also good.
Okay,
but
fine.
In case of gas sensing, TiO2 is not suitable. Zinc oxide is good enough.
Okay.
CDO is for the band gap engineering, the main purpose is this.
Okay, fine.
Okay,
thank you.
So
Thank you so much.
Let us thank Professor Purohit for his nice lecture. So thank you, sir.
Thank you.
Now the third lecture is by Professor Prabhakar Singh. So let me introduce the third speaker of this session. So Professor Prabhakar is currently a head of Department of Physics, IIT BHU. He did his MSc from BHU, MTech from IIT BHU, and he is currently a reviewer of various national and international journals. He attended more than 40 conferences to his credit. He visited various foreign countries like Germany, Poland, France, Greece, and many more for his academic and research purposes. He is member of various national and international societies. He guided various PhD students, and his research interest is basically application of solid oxide fuel cells, solar cells, piezoelectric and dielectric applications. Today, Professor Prabhakar is going to talk about photovoltaics and hysteretic photoconduction. With this introduction, I would like to request Professor Prabhakar to deliver his lecture. Sir, kindly deliver your lecture.
Yeah, thank you. So thank you for a nice introduction. Am I audible?
Yes, sir. Yeah, you are audible.
Yeah, okay. So as I said that, let me first
kindly share your slides.
Wait. Tiwari ji, is it visible?
Your slides are still not visible, but we can see you.
Yeah, of course, but how to show this? Actually, this is the first time I'm delivering a talk on webinar. How to take the presentation on the screen?
There must be one option to share the slides. Means
yeah, this is the
sir. There is an
right.
There is an option present now. Yeah, you may click that.
Yeah, I'm clicking. Yeah, and then
after that, there is an option entire screen or
a window or a
you may select you may select entire screen, and
right.
then it will be available to us.
Okay, I shared. So, are you able to see?
No, still not. The first present now. After that, there must be some screen on your desktop or laptop. There you have to select entire screen.
Yeah, I selected actually. I selected. Are you able to see?
Yes, sir.
Yeah,
now it is working.
Now it's coming.
Okay. Okay, but it is just showing that you are presenting to everyone. Is it? Are you able to see?
Just yes. Now we are
able to see your desktop screen.
Entire screen is visible to us.
Oh, but I am not able to see. Wait.
So kindly hide that.
Right.
Yeah.
Is it okay?
Make it full screen, sir.
Yes, sir.
Yeah,
Yes, sir.
it is fine now.
Yeah, thank you. So my talk is on photovoltaics and hysteric photoconduction. Basically, our group is working in many dimensions of the materials science and technology, where we work on the materials which is useful for the energy applications, like the materials for the fuel cells, materials for the solar cells, materials for the electric materials, ferroelectrics, and the dielectric materials. So one of them is the photovoltaics and hysteric photoconduction. This is our recent work actually. So I have planned actually my whole talk in two parts. One is useful to the students, as I can see that there are many students who are attending this conference. Very nice. And our recent publication, just 10 days earlier, we published this part, which is in Journal of Applied Physics. So I would like to share that part. So it includes basically the research as well as the some fundamentals. So this is why I chose this topic as a photovoltaics, which covers the fundamentals, and the hysteric photoconduction, which is basically the research part which I would present. So now let us start with. So again, as you know that the now there is a mismatch between the energy consumption and energy supply, and we need more and more energy every day, of course. And you can see nowadays the growth of the fuel prices nowadays in India and everywhere. But of course, we need to have a match between the supply and the requirement. So in this way, how can we match this? And if you keep on consuming the whole fuel, this oil, which is dependent on the fossil fuels, I mean, like petroleum, diesel, and natural gases, of course, there would be scarcity, and after a few years, let us say maximum 50 to 60 years, they will be at the peak, and then they will decline. So and our demand is daily by daily it is increasing. So we have to match it. So and also you know that more and more energy, the fossil fuels we will use, we will contribute to more and more hazardous gases to the environment, carbon dioxide, sulfur dioxide, other gases. So what are the solutions actually? How can we control it by without disturbing, without affecting our growth actually? Because every country, every people wants to have advancement in their life. So particularly you can see that there are solutions which is R cube solution or 3R solution, that is the recycle, reuse, and reduce. So you recycle the things which you can use, reuse again, and then reduce the carbon emission and the fuels if you reuse certainly. So this is the philosophy behind the talk, and I just chose this point to use means how we can uh, utilize more and more natural resources instead of fossil fuels and the things. Okay, so if you see the options available, so you can see that there are mainly many options, of course, but if traditional energy resources we can use, they are the fossil fuels, petroleum, diesel, all other things. And then another option is nuclear sources. Of course, they are very good choice, but you know that there are many risks, and of course in the nuclear um, the you need a lot of huge amount of money, huge amount of security, huge amount of the land, and then of course the last but not least, you need to have a very good means the safety, the nuclear waste, how you can dispose it, how you can dispose it. So all these things, if you see that what are the sources, the other sources are the non-conventional energy resources. And the non-conventional energy resources, they are uh, there are many, solar energy, wind energy, geothermal, and all of them. So one of them is, which is the major part, which is the solar energy. So how to utilize it? Okay, so before we become very encouragement, we have a very lot of encouragement to use solar energy. Let us have a rough estimation. I am showing on your screen that if you see the sun, it has a radius of about 13.9 10 to the power 5 kilometer. The outer temperature is about 6,000 Kelvin. The center temperature about 20 million degrees Celsius, and or Kelvin, you can say. The rate of energy, and if you see the rate of energy which is being emitted from the sun is about 3.8 into 10 power 23 kilowatt. Okay, and a very tiny fraction, very tiny fraction of this amount is being collected by the earth, and you can see that it is only 1.7 into 10 power 14 kilowatt. And now let us have that this amount is available to the earth. This is this energy, of course, the kilowatt, the rate of energy, I mean, which is available to the earth. If you see the world population, if you assume that it is 10 billion, which is of course not yet, with the total power need per person of 10 kilowatt, let us say that each person needs 10 kilowatt energy, means power, then if you calculate it, then you would need about 10 power 11 kilowatt of energy. Now you have this much energy need. Your need is this. Now, if you assume that you can convert the total energy which is being received on Earth, 1% of only this energy, if you are converting to the useful energy with the device of having 10% efficiency, then you will find that it is sufficient to fulfill the need of the each and every person on the earth. It is very encouraging, of course, but again there is a but. That is that there are physical, technological, socio-economic, all these limitations which we need um, to overcome actually before we think in this direction that the only solar energy would be one of the best. I mean, only solar energy would be the option. Okay. And if you see the sun, and you talk of all the energy, you can see the solar radiation is basically, you can collect it technologically and naturally, you can also collect it naturally. So natural collection, photosynthesis, which creates wind energy, of course, the ocean temperature difference, and you convert it to the useful energy. And you have also the technological collection, that is the you can collect it thermally, thermal for the thermal application, for the thermal collectors, are the photovoltaics, that is for producing the electricity. So you can see that almost all the sources on the earth, the energy sources is only sun actually. If you use wind energy, wind is created due to the pressure difference, and difference is created due to the temperature difference on the earth surface, and that is created by the sun only. So this means that means almost all the resource, even if you talk of the fossil fuels are basically, fossils are basically thousands and thousands years ago. They are the trees, plants, and the fossils. They are burnt off, and then they are basically converted into the petroleum and diesel. So where did they get their energy from before, when they were live? It is only from the sun actually. So you can see that almost all the resources are available due to the sun only on the earth. So now our main topic is photovoltaics. As I said that we can collect technologically the solar energy through the thermal and the photovoltaics. And you know that solar radiation, the major component is the about 50% is infrared, microwave, and lower part, and about 50% is visible, ultraviolet, and other parts of the in the radiation. So the infrared and other parts, the lower part of energy, you can use for the heating purpose, the thermal purpose, and ultraviolet and the visible regions you can probably use for the photovoltaics application. So what is photovoltaics for the students? It is simply you just put a light on the surface of some material, and you will see the current in the outer circuit. So it is certainly not exactly equivalent to the electricity or the emission of electrons, that is photoelectric effect. It is certainly different than that. So what are the conditions you can make it useful for the photovoltaics application? So I just explain it through a very simple model that is basically showing you the fundamentals. You see that you have p-type semiconductor and n-type semiconductors, and in p-type you have majority charge carriers as a whole, and in n-type you have electrons as a majority charge carriers. And when you make a junction, of course, because of the concentration gradient, the majority charge carriers from n goes to p side, and from p, the holes from p side goes to n side. Now that is stopped after certain interval when the equilibrium is reached. But what happens if you see that there are the holes in the n side as a minority charge carriers, and there are electrons in the p side which are the majority charge carriers. Now, if you see this field E field, which is basically the depletion layer created, the majority charge carriers from the minority charge carriers from n side, when they come into the influence of this E field, they will simply sweep to the p region. Similarly, the electrons in this region, they will simply come to this region, they will go to this region. But it is not true for the majority charge carriers. Now, just keep it in this mind, this point in mind. Let us go to the illuminated junction. When junction is illuminated, what is happening actually? Means when you expose the junction to the light, the appropriate energy, of course. So you see that in a semiconductor, the majority charge carrier concentration is about 10 to the power of 20, of course, per centimeter, which is very high. The minority charge carrier concentration is about 10 to the power of 11. And when you put a light on this, the electron hole pairs are generated, and their concentration is about 10 to the power of 11 per centimeter cube. This means that this is affecting the concentration of only the minority charge carriers, not the majority. You can see the magnitude actually. It is still 10 to the power 9 order of magnitude higher, 1 billion order of magnitude higher. So it is not affecting the majority charge carrier concentration. Now, when the light is there, the electrons from the p region, which are the minority charge carriers, it will come to this band, and this will go simply to this region. Similarly, the holes from the n region, which are the minority charge carriers, they will come in this field, and they will go to this region. So this is a kind of hole drift to this region and electron drift to this region. What would happen that when it is illuminated with the proper band energy, and in this side, in the p region, electrons, the holes will be accumulated because of the transfer of holes from the n region to this region, to the p region, and this side, the electrons will be accumulated because these electrons are simply shifting. Of course, there are many things which neutralizes them. The recombination process, the trapping of the charge carriers, they are of course there. This is why the efficiency is very low. So you see that here there are positive charges as a whole, and here negative charges as a whole, as electrons are connected. So this will create a kind of voltage difference because of this polarization of charges, and this voltage is known as, this effect is known as, the creation of the voltage is known as the photovoltaic effect, the generation of the voltage. Now, when you simply connect with a wire in this situation, of course, in the lightning situation, the holes will go from this side to this side, and they will recombine with the electrons, and they keep on going, and then you will have electricity in the outer circuit. Or in another word, you can say the electrons can leave from this side to this side, and they are recombining at this point. So this is simply working as a cell. What is the requirement of a cell? The cell is basically a device that generates energy. So here this is basically generating energy without any internal consumption of any other source of energy. Only you need to illuminate it. So you see, when you make a curve of a IV curve of this semiconductor curve, you know that the forward bias condition in this way, and in the reverse bias condition, and the dark current, this is the dark current which is going on, and when you increase the intensity, or you just illuminate it, this is dark current means without illumination. When you illuminate it with the proper energy of frequency of the light, you will have a current actually in the outside. And when you keep on this increasing to this coordinate, you will find that this is going to this way. So this means if you calculate power, for example, in this quadrant, the first quadrant, what would happen? V is positive, I is positive, so P into V would be positive. So this means that power is positive. In the third quadrant here, what is going on? You see that V is negative, V is negative, and I is also negative. So when you calculate power, again P is equal to V into I, again you will be getting the positive power. But in the fourth quadrant, what is going on? You see that V is positive and I is negative. This means that in this quadrant, when you take a power, P is equal to V into I, you will be getting a negative power. So what is the meaning of positive power and negative power? Positive power means you are consuming power from the external source. And negative power means just opposite of this, means you are delivering power to the external source. So here in the fourth quadrant, the system is working like a cell, and that is known as solar cell. So please remember that the solar cell is always working in this one. And you see this in third quadrant. The third quadrant, if you increase the intensity, this will go more and more down. This means that this is going more and more down. I'm not sure that able to see because okay, you see the third quadrant. So the current will increasing in the negative direction. So this means that it can work as a photo detector in this quadrant. You increase the intensity, you can calibrate that at this current, this is the intensity, this current, this is the intensity, and you can have a very good sensor that detects the different intensity of the light. Right. So this is the way you can work. And I'm not going to the mathematical calculation and all these equations, which is simple. I is equal to, this is the diode equation, and this is the light generated current, and this is what the total current is this. So the various parameters you can calculate. I have just, for the sake of simplicity, because our idea is always to look the things in a positive way. So I have inverted the I-axis. V is same. I have just rotated it by 180 degrees Celsius. So I here on this axis is negative basically. So you can see that with maximum, you can calculate the maximum power, all these parameters you can calculate, and probably you are all knowing this. So I will not take much time to how to calculate it. So this is, you can do it. The fill factor you can easily calculate by this using. Fill factor is simply that you have to fill this region, actually this region. I'm not able, yeah, you have to fill this region. This region is basically showing you that as much as you are closer to this point, your efficiency will be more and more. This means that you will be able to deliver and receive more power from the solar cell, and this if affects the enhance your efficiency too. Now, photovoltaics basic structure, apart from that was the semiconducting part we were discussing. If you consider a photovoltaic solar cell, the three main parts are there. You have a light absorber, that is the junction part, which is basically in the semiconductor point of view, that is absorbing the light. Carrier collector, the both sides, besides your depletion region, that indicates the carrier collector. And then metal contacts, of course, you need to have external metal contact to have a current in the external circuit. As I said, the efficiency is still very low. The highest efficiency theoretical is, of course, more than about near to 50%, but experimentally it is still 25, 26, 26%, or you can say, yeah, of course. And then this is basically because of the poor collection of the charge carriers, the high recombination rate, low lifetime, low penetration depth, all these things, the factors which is very important, which needs to be taken care when you make it a solar cell. Okay, so as I said that you need to have a light collector, you need to have a light receiver, and you need to have a light distributor. Okay, so just go to the history. There are three generations of solar cells: wafer based, which are the monocrystalline silicon, which is long back, and you can see the efficiency is high. Polycrystalline silicon, multi-junction cells, they are the first generation. And the second generation, you have the thin film. The same thing, the crystalline form has reduced to the two-dimension amorphous thin film, cadmium telluride, and copper, indium, gallium, selenium, all these materials, you can make a thin film and you can have a two-dimensional solar cell where you can wrap it and you can use it even on at a screen of window screen. Okay. Low cost and high efficient, the fourth generation, the dye synthesized quantum dot, the third generation, of course, the quantum dot sensitized organic photovoltaics and polymer hybrid solar cell. Now, the about in 2014, I think the perovskite solar cell actually that came into the picture, and many lot of work has started in this field because you can see the growth actually. The solar cell current status. This is the graph. I think most of the solar cell or the solar energy people will be showing you that here you can see the from starting from the 1975 to 2020, the whole data is given, and you take any type of solar cell, you can see they are growing very slowly. But this, you see, this that started as basically in 2014 around, and it has a sharp rise. And this is the perovskite solar cell. You can imagine that in last 5 years, 6 years, means I think 10,000, 15,000 papers would have come, and of course the lot of citations are there. So because of this, the people started to work on the perovskite solar cells. And why perovskite? Important question is why perovskite? Because as it is mentioned that high charge, it has a very high charge carrier mobility, long charge carrier lifetime is more, so that it can penetrate into the other side of the system, and it can go to the whole transport layer or the electron transport layer without recombining, without being neutralized. And high open circuit voltage it provides, the band gap can be adjusted because of the you can make different types of doping, and low cost fabrication, of course. So this is a simple the perovskite solar cell, the schematic of the perovskite solar cell. It is the light absorbing material. This is the whole transport layer, which is the electron transport layer, electrodes, and just to connect to the external circuits. And of course, there is a question: what is the role of perovskite? Because here there is no physical junction, no semiconducting junction. So basically, it is the band alignment scheme. You have the band alignment, you have to choose whole transport layer, the electron transport layer, and the absorbing material in such a way that in the conduction process, when the light is falling, the Fermi level basically that when it gets disturbed, that are aligned, so that the transfer of electrons takes place to the electron transfer layer, and the transfer of holes can take place to the whole transport layer. So this is basically the band alignment scheme they are working on. Perovskite, you know that it is a very well-known material, and the people from long time the people are working, and this is a kind of ABX3 type of material, and from the solar cells point of view, the perovskite solar cell point of view, the CS3NS3, that is the Ma, that is the methyl aminium, and this is Fa plus cesium, and all these materials you can, even the inorganic materials you can also add as a at the place of A actually. Okay, the problem was, what is the problem? If the solar cell, the perovskite solar cells are very well and everything is working very fashionable way, and the things are moving in a very well direction, so why do we need so what is the problem? Let us use it. So, but of course, if it starts, there are many if and buts. People are trying to improve the qualities and decrease the disqualities basically. So with the perovskite solar cell, the basic issue is its stability. It is very sensitive to the heat, light, moisture, and oxygen, basically. And you can see all the pillars are set, but stability is still there are the obstacles, that is the light, heat, and humidity, which is pulling back the stability factor. This pillar needs to be established properly. Okay. Now I did that was the first part, that is the basics of the photovoltaics for the students, and what we worked actually in our lab actually. As I said that we started this work, doing work about 4 years back, and we have still not very sophisticated lab. So we are trying to optimize the materials properties, and we are trying to see what properties could be helpful to make it more useful, efficient, and useful solar cells. And if even though means we are also trying that what properties or what qualities or what the factors which are affecting the efficiency of the solar cells. Okay, so we basically in our lab we prepare the samples through the simple method, which is solid state route, and we do it through the cold sintering. Cold sintering means it is sintered at room temperature, because they are, as I said, that they are very nice preparation samples. And uh, this, for example, I took it MAPBI3, which is which is the organic absorbing material for the solar cell. We tried to measure current and voltage, and you can see that 0 minute, 10 minute, 20 minute, and 30 minutes, and we found that it is going down with time. Dark current, of course, very low, but when you put light, current increases, but it is going down. So of course the degradation is there. It is not stable actually. The material is not stable, and you can see the degradation within 10 minutes of light exposure, and this is the photo instability we observed actually. However, when we prepared, instead of organic solar cells, organic material, we put CS actually at the site of MA. And when we prepared the sample, we found that CSPBI3 instead of MAPBI3, it is very well stable. You can see the XRD, which was taken fresh, and then after 100 days. And we did not put it in any glow box or any inert atmosphere. We just put it in a box and seal it properly. And after 100 days, we measured. So structurally, it was stable. You can see this one also. The pressure after exactly XRD is matching. We also measured its band gap, and we found there is very little effect of band gap after 100 days, which is negligible. Basically, it was about initially it was 2.27, and after that it was 2.28. So very little. The second decimal place it is changing. So we found it stable, and of course nearly 1 year it is passed, means we have a sample, and we tried to see it, and we found there is no change. Okay.
Prabhakar sir.
Yeah.
So time, please.
Yes, I started at about 11:40.
Okay.
And you gave me half an hour. I will not use more than half an hour. Be assured.
Okay. Okay, sir. Okay.
Okay. So photo current instability. We saw it actually the photo current instability, because as I explained that earlier, that when we put the light, it was degraded, and the material was degraded. So what could be the reason actually? Photo instability, of course, because of the degradation in the structure, and hysteresis. Hysteresis is still, this is the puzzle. People are trying to look into this side, and hysteresis, they are trying to explain it, and still the satisfactory explanation has not yet come actually. So we started to think in this direction in the hysteresis, and now we prepare the thin films of the material, the CSPB BR3, and through the pulse laser deposition system, pulse laser PLD, recently established in our department last year only. So we looked into this matter, and we deposited the thin film, and we tried to take the measurement. Yeah. And when we measure it IV curve, and we found that, of course, because this is not the cell, actually only we take CSPVR3, we did not put any electron trapping material and the whole trapping material on the both the side, and then we tried to measure IV curve, the bare material of CSPVR3, and we found a bit current, which is you can see on this fourth quadrant. Of course, they are very low, and if we make a cell, and if we are able to make it stable, of course, we will be getting the photo current. Electrical studies, we made it, and we found that, of course, there is a chances to make this material to choose as a absorber material to the active layer material for the solar cell. And you can see this is the basically we found it as an artifact because we put this much voltage across this, and then we found this current actually. So uh, uh, now we also tried to study the bulk pellets by the solid. We prepared the bulk pellets by the solid state reaction route, and we calculated the band energy, the CS, and we tried also to work on lead free material. That is, we replaced PB with SN, and we found a very good band gap, 1.7 electron volt, which is very useful. Even it is in the visible region we can use for this band gap actually. Okay. Uh, and this is the stability. I think it is checked. Yeah. So now we made the IV curve measurement on the IV measurement on the pellets basically, and we found that even in the bulk sample CSPVR3, the photo degeneration is observed as evident by the increase in the hysteresis area. You can see that what we did actually, we took the sample and we put light after half hour interval. So you can see up to 3 hours we take six times measurement, and then we plot it here at different times, and we found that the hysteresis area basically which is increases. We have just plotted the hysteresis area here. So, and we published this paper recently, I think 10 days earlier, this published in our Journal of Applied Physics. So you can see that this hysteresis area increases with increase in time. And we calculated basically, just try to understand what is the reason why the hysteresis area increasing, what are the charges which are being created in the system. We used the Drude model and we calculated the parameter k and n of the equation. Je is equal to ke to the power of n, and we found that is increasing and then becoming constant, and they are here k, and they are basically related to the generation of charges, the photo charges in fact, and the mobility of the charges. So here we found that the mobilities decreases, the k represents basically mobility and n is the generation of the charges. So this is increasing basically. And we calculated sigma, and this creates that xi. This explains, this gives us that you see that here the fs stands for the forward scanning and reverse scanning for the rs actually, and this is the time when we expose the light, and before 0 it is basically without light measurement. Effect of light, we put the light pulses actually. You can see the yellow region which is light pulses, and then bias voltage with the 5 volt and 2 volt we increased, calculated, and we found that it follows a homogeneous distribution of the excitants which are generated actually, which are in the form of polarons in the system which are generated. And when we calculated the transference number of this material, it was about 0.72. That gives you a second type of the ionic conductor, that is the mixed ionic electronic conductor. And we confirm it through the PL measurement, and then this also confirms that there are excitons which are created, the photo-generated electrons and the polarons basically. And to know the nature of the polarons, we try to study the material, the ion dynamics of the material, and from the ion dynamics, we found that it is the small polarons which are generated because of the light actually. And this is the model which we explained, and we found that basically it is the barrier which the grain and grain boundary barrier in the system, because we are using the bulk sample in a pellet form, which are creating and trapping the charges, and which are basically generating the excitons in the system. We calculated the density of the state also, and we calculated from the same, we calculated also the epsilon, that is the dielectric constant. And now I conclude, of course, the defect contains, for example, interstitial lead acts as a mobile generating center, which under a combined action of photo and space charge limited injection can capture electrons from excitons and provide a free holes for the conduction. So this means that lead +2 in the CSPBr3 is which are responsible for generating the holes, and which are creating the excitons and the polarons. In summary, from the present study, it appears that reported mechanism of the hysteresis, that the trapping ion migration polarization and slow capacitive current are interrelated. And the photocurrent voltage hysteresis is primarily affected by the thermionic field emission caused by the infrared light part of sunlight with the H nu. So this is we conclude with that the hysteresis is basically the hysteresis area is basically generated because of the excitons and the polarons, the small polarons which are being generated due to the light, and they are responsible for the losses in the conduction process. So wait a minute. So thank you to the organizers for inviting me, and thank you for your patience, patiently hearing my talk. Though I don't like this webinar, but this is nowadays our kind of, you can say, we have to follow this because of the social distancing. So this is, thank you so much. And this is my research group which is working. These two are my postdoctoral students, and back they are my PhD students, all PhD students working on this. And this work is Manish, actually he performed this work, and this Prem, Manish, and this Ashish, they are working on photovoltaics. Vani, and yeah, Vani has completed PhD, and she got degree. So on photovoltaics, Vandana, Manisha, they are working on fuel cells, Swarnima, and so thank you so much to my students. Thank you.
Thank you, sir. Thank you for your nice, informative lecture. So the forum is open for any question and discussion. Anyone would like to ask questions from Professor Prabhakar? Any question? Sir, I am having one question.
Right.
For how many cycles these materials can be used?
Basically, as I said, that they are very much unstable to the photo lights. So up to 3 hours we used it, and for the CSPBr3, and they were working. And but I think it is not working for more than 5 hours, 6 hours. Of course, there are problems.
Okay. So let us thank Professor Prabhakar for his nice lecture. So thank you, sir, once again. Thank you for this lecture.
Thank you very much. Thank you.
So now Adarsh is around, Dr. Adarsh.
Yes, sir.
Yeah. So
Thank you.
thank you for giving me this opportunity to chair this session. So now I hand over this to you and for further proceedings.
Thank you, Anil sir, and you have done your job, and wonderful job, I should say. And
we are late, actually.
thank you once again. And now to move forward, I would like to invite Dr. Nandan Best. He is a assistant professor in Kumaon University, Nainital, and he has, before joining this Kumaon University, he has done his PhD from NPL And after that, he moved to UEC Tokyo for doing his postdoc. And his field of interest is applied optics and quantum optics. He has published more than 20 publications in reputed journals. So I would like to invite Dr. Nandan Best from Kumar University to chair this next session and invite the guest and proceed forward. Please.
Thank you, thank you, Dr. Adarsh, and welcome to all in this final session. And in this session, we have 3 plenary talks. And I think Professor Birpal Singh is not available now. So I will be moving forward now. The next talk is from Professor Ujjwal Sen. And let me introduce a speaker of this plenary talk. Ujjwal Sen is currently a professor of physics at HRI Allahabad and works in the quantum information and the computation and its interface with other areas. He did his schooling, college, and the university in Kolkata. And his PhD was with Rizat Rotsky in Gansk, after which he was a Humboldt Fellow with Mrs. Levenstein in Hanover. He was then a Roman Y. Castle Fellow with the Mrs. Levenstein in Barcelona, and he was briefly an assistant professor in physics at IIT Delhi as well. So now I invite Professor Ujjwal Sen. He's talking about the quantum devices using systems with the impurities. And sir, you'll be starting at 12:20 around. So the time is 25 for talk and 5 minutes for the discussions.
Okay, thank you. So should I share the screen?
If possible, I think it would be better because...
So where is you know where the share screen is? This present now? Is that the one?
Yes, by using present now.
Okay, okay. Present now. Entire screen. Okay. Yes. Yeah. So can you see my screen?
Not yet appeared.
No, it's still not.
I have shared it. Mm-hmm.
After selecting present now, yeah.
It is now. Yeah, yeah, it's done.
Okay, okay. Yeah, okay, okay. So now I will. Yes. So can you see my screen?
Yes.
Yeah. Okay. Okay. Yeah. So thank you. It's a pleasure to give this talk, and thank you for the invitation. I hope sometime later, when this problem of the lockdown goes over, I will be able to visit your place. And I would invite you also to come to our institute. And so our institute is in Allahabad. It's just a little bit outside Allahabad. And here we have a quantum information and computation group where we work on aspects of this subject and its interface with other areas. So today's talk, I will be telling you about quantum devices, quantum-enabled devices in systems which has maybe some impurities. So So what are quantum devices? They are devices in which you use quantum laws to run them. So examples are quantum computers, quantum cryptographic devices, and many others. Some of them are in the market. So for example, quantum cryptographic devices you can buy in the market, but some are not. For example, quantum computers are not yet available in the as a device that you can use. But there is hope that within some years it will become available. This is not clear as yet. In many of these devices, but not all of them, the diesel, the thing that is used as the resource for these devices is something called entanglement. So I will not give you a formal definition of entanglement. I mean that will take some more time and some more algebra. But I will try to give broad definition of it. So we will somehow have a cartoon of the definition. So let us, in our mind, think about two worlds. One world is a world of small letters, small a, small b, small c, etc. And there is another world which is the world of capital letters, so capital A, capital B, and so on. And now consider this in the second line, I write this A into capital A plus A into capital B. And now such expressions we all have learned in school, and we know that, I mean, in our first chapter of algebra, we have learned that this can be factorized, and you can write it as A into capital A plus capital B. There can be more complicated expressions, like in the second line, and you do some tricks with it, and you can show that this can also be factorized. But there are expressions like this one in this A into capital A plus B into capital B in the fourth line, if you see, this cannot be factored. This cannot be factored into small letters, an expression of small letters multiplied by an expression of capital letters. And we have all seen such expressions in school. And this is a very simple fact. The point that I want to make here is that this simple fact, when carried over to something called tensor product Hilbert spaces, provides the opportunity of having entangled states. So you have to think of the world of small letters as a physical system, let's say the polarization of a photon, and the world of capital letters as another photon whose polarization we are considering. And then between these two polarization systems of photons, we can have entanglement. Such entangled states can and has been prepared in several physical systems in many different, in a large number of laboratories. And moreover, such entangled states, once prepared, they are actually useful. So this is my definition of entanglement. Of course, this is not very mathematically precise, but we will, because of the restrictions on time, we will sort of accept it. So we have defined in a hazy way that what is entanglement. Now, once we know that a state is entangled, one can try to measure it, how much entanglement is there. And then again, there are many different measures of entanglement. And again, we will not define them. We will use such measures of entanglement in the talk, but we will not go to the definition. Okay, so we go forward. So one of the main things of this talk is the impurities. So we will handle systems that has impurities in it. And now, as we all know, impurities are everywhere, whether you like them or not. And interestingly, there are recent attempts to engineer impurities in artificial materials. And why do we want to do that? Well, because creating disordered or doped systems leads to having controllable impure systems. And then it makes the studying of phases of such systems quite easy. This is the first point. And the second point is that impurities can sometimes, though not always, be useful, in the sense that there are systems which does not magnetize if there is no impurity, but it becomes magnetizable once there is some impurity in it. So with that, we will go to my list of topics that I hope to cover. So we will discuss about something called glassy systems. So I will define what does it mean by a glassy system. And there are two types of glassy systems that we will consider. One is the single and double Jaynes-Cummings model. So I will define, maybe many of you know what is a Jaynes-Cummings model. I will tell you the definition in the coming slides. And the other topic that I hope to cover is the glassy disorder in something called a quantum random walk. I will define all these terms as I go into the talk. So we begin with the first topic. It's a glassy single and double Jaynes-Cummings model. So this is the Jaynes-Cummings model. It's a very simple model of a two-level atom. I mean, there are no atoms that are two-level. Atoms have a huge number of levels, but we are considering a situation where it is possible to somehow isolate two levels of an atom. And we call that a two-level atom. And that is kept in a single mode cavity. And again, this is a difficult thing to do in practice, but we assume that it is possible. And then we also assume that the interaction between this two-level atom and the single mode cavity is given by this interaction Hamiltonian. So the, this term H bar is H bar, and this G is the interaction strength. And this A and A dagger are operators of the mode system. So they are destruction and creation operators of the single mode cavity. And the 0 and 1 are the levels of the atom. This is actually a very famous model, very simple model, but it's a, in cavity physics, it is actually very useful. And now this picture, we drew it in our system, but in our computers, but it is a very old picture. People have worked on it for tens of years, for decades now. It's something called the population inversion in the Jaynes-Cummings model. It's essentially the magnetization of the atom in the Jaynes-Cummings model. And this axis, the horizontal axis is the time, and the vertical axis is the population inversion. And as you see that there are collapses and revivals in the population inversion. And this has been theoretically seen and also experimentally checked. Now, this figure is also known from some time, not as old as the previous picture, but this is also, I mean, we have drawn it in our computers, but people have drawn it in their computers for a long time now, maybe 10 years. And there are also experiments that have checked this. So this is here, the horizontal axis is again of time. The vertical axis is, however, the entanglement between the atom and the cavity. So this is the atom cavity entanglement. Again, I have not mentioned the measure that I am using for quantifying the entanglement, but they are qualitatively, they all look similar. The quantitative features may change a little for the different measures, but they all look broadly similar. And you see that there are, again, collapses and revivals in a different sense also in entanglement. So now in this system, this Jens-Cummings model, we will try to insert some amount of disorder. So for that, we digress a little. We go to a different, for a few slides, we discuss about something called quenched disorder. Now, impurities, I told in the title of the talk that I will be talking about impurities, but there are different types of impurities that can appear. And so, for example, in some systems that you try to prepare, there can be missing particles, or there can be disordered system parameters. We will be considering disordered system parameters. Now, disordered system parameters can also be of many types. And of that, among them, we will consider something that is called quenched disorder. And what is quenched disorder? This is what we will discuss now. So it's usual to call quenched disorder also as glassy disorder. So what is the meaning of this word, glassy or quenched? The point is that these disorders equilibrate long after all the relevant observations are over. So I am making some observations on a system, and that system has some disorder. That disorder will equilibrate after a long time, but that long time is much longer than all my observation times. So physically relevant quantities are the quenched averaged physical quantities. So what does it mean by a quenched average physical quantity? So what we do is that we find the value of the physical quantity, let's say magnetization or entanglement, for a given realization of the disorder. And then we average over all possible realization. So this order of doing the average and the finding the value is very important. So we first find the value of the quantity and then do the average. And this is what is called as quenched average. So to give you an example, this is again a cartoon. So this is a settlement of people, and there are, and it has happened randomly over a long period. But now I want to find out how many girls in this neighborhood play football. And now I will take some time to find it. This is a huge place and there are many people living here. So I go from door to door, and suppose I take 1 month to find this out. Now, during this time, 1 month, that is my observation time, almost nothing changes in this neighborhood. The number of people is almost constant. The number of houses is almost constant. But now, once I find this value of the number of girls who are interested in playing football, I can now try to find the same value for a similarly realized neighborhood. And this, finding the value of the number and then doing the averaging over different realizations of this neighborhood, is called quenched average. So this is our glassy Jens-Cummings model. It's the same model, if you notice, the one that we had before, except for this factor 1 plus delta. This delta is a random variable. It's a quenched disordered random variable. It will follow a certain probability distribution that depends on the actual realization in the laboratory. Let us begin. Everybody begins with Gaussian distributions. So I also began with that. So So what we have here is a Hamiltonian between an atom and a photon and a cavity. So it's an atom and a cavity. And there is a factor 1 plus delta in the interaction strength where this delta is disordered. So different realizations of this system will have different values of this disorder, but they are not completely random. They follow a certain probability distribution, and that is, first of all, we consider it to be a Gaussian distribution. This is my system that I will deal with. And now we consider the same two figures that I had shown you earlier. Remember those two figures? So the horizontal axis is again time, and the vertical axis on the left-hand side is the population inversion, is essentially the magnetization of the atom, and the entanglement between the atom and the photon on the right-hand side, on the x-axis, on the y-axis, on the vertical axis. But in the previous pictures, on the vertical axis, there was no disorder in the system, so we just took for a single realization of the interaction strength. But now there is a disorder in the interaction strength. So this time in these two figures, the vertical axis are quenched averaged magnetization and quenched averaged entanglement, where the distribution is Gaussian. Now, if you look at the left-hand side figure, you will see that, so look at the numbers on the x-axis, on the y-axis, you will see that they become very small. So, for example, when the time is at 10, the vertical axis runs from -2 into 10 power minus 9 to 2 into 10 power minus 9. So, these are very small numbers. So, what has happened is that the value of the magnetization has become very, very small as we go to larger and larger times. And let's say at time equal to 24, there is almost nothing left. So the quenched averaged population inversion, the quenched average magnetization, has been squeezed to almost zero by insertion of the disorder. There is almost no collapse and revival feature left in the system if you insert some disorder into the system. But now look at what happens to the entanglement. In the entanglement, if you go to larger and larger times, let's say at the same point and 24, on the left-hand side, the value of the quenched averaged population inversion is around 0. But at the same point, at 24, if you look at the third figure and the third panel on the right-hand side, you see that the entanglement is close to 1. So, although the Gaussian disorder destroys almost all of the population inversion with time, it is unable to destroy the entanglement with time. Entanglement survives, the atom-photon entanglement survives with time. There are no, the oscillations have gone away and entanglement has stabilized to a value that is very close to 1. Yeah, so this is what I wanted to say, that even after the oscillations in population inversion have died out, atom-photon entanglement continues to oscillate appreciably, and its value is very high in comparison to the population inversion. So the new parameter that we introduced was this delta, and the previous figures were for Gaussian disorder. But we have also considered other disorder distributions, and they can significantly alter the behavior. So let us see. So we go to some non-Gaussian disorders, and this was the Gaussian, and now I am showing only the atom-photon entanglement. So this was for the Gaussian. But now if you take a discrete disorder distribution, this is the distribution. It is qualitatively quite similar, but quantitatively different. If I take an uniform distribution, this is the picture. And there is something called a Cauchy-Lorentz distribution, where we were using something called median-based averages, and there this is the picture. So as you see in all these 4 examples of disorders, the qualitative features are more or less the same, but quantitatively they differ in values. Now I will move to, so how much time am I left with? Hello?
8 to 10 minutes.
8 to 10 minutes, yeah, okay, I'll continue. So we have considered until now what is called the Jaynes-Cummings model. It's essentially the single Jaynes-Cummings model. What do we mean by single? It means it's a single atom and a single cavity. Now we will change our topic a little, and we will consider something that is called a double Jaynes-Cummings model. So a double Jaynes-Cummings model is 2 cavities and 2 atoms inside it. So if you look at the first line here, it's essentially a single Jaynes-Cummings model, and the second line of the Hamiltonian is another Jaynes-Cummings model. I mean, so the first line has the atom A in the cavity that has creation and annihilation operators as A and A dagger. And but we also have another atom that we denote by B, capital B, and which is kept in the cavity in which the creation and annihilation operators are denoted by small b and small b dagger. And there is no interaction between the atoms and no interaction between the 2 cavities. So this is a Jaynes-Cummings model in which we have 2 separate cavities in which there are 2 separated atoms kept. These atoms are considered to be 2-level. But the 2 atoms that are there in these 2 cavities have previously interacted with each other and have created a state that is written at the bottom of this slide. This is cos alpha 1a 1b and sin alpha 0a 0b. This is an example of an entangled state, and you can show that you cannot write this state as a product of 2 different states of the 2 atoms. This alpha is essentially can be considered to be a entanglement strength. This 1a and 0a are levels of the atom A, and 1b and 0b are levels of the atom B. So now we consider the evolution of this system when we begin with this 2-atom system. And this again is not a curve that I have plotted this, our students have plotted this, but this is well known from quite some time, maybe 10 years now. And if you look at the bottom figure, on the horizontal axis there is its time, and on the vertical axis it has entanglement. The measure that is used is something that is called concurrence. I have not defined it. So it is a measure of entanglement, the entanglement between the 2 atoms. Remember, this is a different entanglement than the entanglement that we have considered in the previous slides. For the single Jaynes-Cummings model, I have considered entanglement between atom and the cavity. Here, I am considering entanglement between the 2 atoms. And now, the important thing in this figure is if you look at the bottom figure, and at a time that is around, let's say, 0.2, you see that the entanglement comes and abruptly becomes 0. Abruptly in the sense that the derivative of the curve is discontinuous. It suddenly becomes 0. This phenomenon is well known for some time, and it has been called entanglement sudden death. There is a the entanglement sort of plunges to 0. It becomes 0 suddenly. The derivative of the curve with respect to time has a discontinuity. This happens also in the upper panel, but let us focus only on the bottom panel. Now, if we consider in the same system, we consider disorder in the interactions. So what we do, this delta A and delta B are disorder strengths that are put in the, so delta A is the disorder in the atom photon, the first atom photon pair, and delta B is the disorder in the second atom photon pair. And if I put, so if you look at the first panel, then you see that there is entanglement sudden death at around the same time, maybe at 0.2 or something, and but at later times the entanglement sudden death vanishes. So if you look at the previous figure, you see that entanglement sudden death is there at many intervals. It continues. It's periodic curve. But once you put disorder, there is entanglement sudden death initially, but then there is nothing. The entanglement sudden death phenomenon vanishes once you insert disorder. And if you put in a stronger disorder, as you see in the middle panel, then the entanglement sudden death phenomenon disappears completely. So what we have here is that disorder in the interaction strength can wipe out entanglement sudden death. The phenomenon goes away once you put disorder into the system. So there is a certain complementarity between entanglement and the threshold strengths of the disorder. Let me not discuss this because I'm sort of short of time. So yeah, so this is there is some sort of a complementary between entanglement and disorder strengths. And so this is the paper, reference to the paper, and these are the students who did all these calculations. These calculations were done numerically in our cluster. So maybe I have 5 minutes left. Hello.
Yeah.
Yeah. So in these last 5 minutes, I will try to tell you about a different system. The same disorder, but in a different system. And this system is called a quantum random walk. Yeah. So, well, this is of course a cartoon. I mean, not a cartoon, it's a picture. But I want to make a cartoon of what I will be speaking. The topic that we will discuss is about a drunk person. This is Johnny Walker. I hope all of you know him. I mean, I am an old person, so he is sort of very, I know him very well, but from his movies, of course. But I don't know, the young students, maybe they don't know him so much. He's an yesteryear actor from Bollywood. So this person is a drunk, and we want to help him walk home. This is the cartoon version of what I will be speaking about. So that is what is a quantum walk. So what is a walk? I mean, walks can be considered in classical case as well as quantum cases. We will. So we have a drunk who is trying to reach home, and we are considering discrete steps. And we are also considering that this drunk is walking on a straight line. So at every step, there are two options available. So she or he can walk forward or walk backward. But at every step, there is no other option. There is no sideways. Okay, so I mean, people have considered also 2-dimensional and 3-dimensional lattices, but here we will consider only a 1-dimensional lattice. So the drunk is walking on a straight line, and at every step, she or he is either walking forward or walking backward, and doing that randomly. At every site, there is a coin that is tossed. The coin is will give you either a head or a tail. Now, suppose that if the coin produces a head, the walker moves forward, and if the coin produces a tail, the walker moves backward. This is what is a classical random walk. A classical, if I consider such a classical walker and a coin, the walker will never reach home. So suppose the walker has gone to some place to drink, and then from there, he or she starts to toss a coin and move backward and forward as the coin is tossed. Then you can show that the distribution of the walker's position is actually a Gaussian. So, Gaussian around the initial position of the walker. So, the walker actually almost never goes home because she or he is moving around that same initial position. You can show also that the variance of the walk. So, the walker's position, as I said, is probability distribution. The mean of that position distribution is the initial position of the walker. But one can also calculate the variance. The variance of the classical walker's position is proportional to the square root of the number of steps. Yes, so if he takes 10 steps, then the variance is square root of 10.
Professor Hussain, now you summarize your talk now.
Yeah. Okay. So this is what is classical random walk. One can consider a quantum random walk where one can say that you can show that the variance is actually better. So in this sense, quantum mechanics helps. So what our work, so I will go to the end of the talk. What we try to see is in the quantum case, what happens if we insert disorder in the system. And if you we show that if you insert disorder in the system, then what happens is that you come in between classical and quantum. So in the classical case, the exponent of the variance was half, and the exponent became 1 in the quantum case. So in this sense, the drunk person has a better chance of reaching home in the quantum case. But if you insert disorder in the quantum case, then you reach a region which is in between classical and quantum, and you reach a point that is around 0.8. The exponent becomes 0.8. So it is sort of a super diffusive but sub-ballistic. It is an intermediate region between classical and quantum. So yeah, so I mean, although quantum mechanics helps, but not too much. And we have also considered different types of disorder. I will not go into that. And these are the people who are doing the work, and these two students and the postdoc. And these are the references. And so this is the end of the talk. And so what we wanted to see was that impurities exist in the system and can also be engineered. And such systems are interesting and can sometimes be useful. And so thank you. And this is the group that we have at Allahabad who does quantum information. Thank you.
Thank you very much, Professor Hussain. Now, session is open for a couple of questions, but so I have a couple of questions. So in the case of this JC model in the single atom and the double atom, what was the difference in a concurrence rate? What was the difference in the single atom and double atom? And what was the, did you check the fidelity as well or not?
No, we did not check the fidelity. So we were interested in the population inversion and population for the single Jens-Cummings model, we were interested in the population inversion and the atom photon entanglement, and there it was pure state, so entanglement was easy to calculate. Whereas in the other case, in the double Jens-Cummings model, we have looked only at the atom-atom entanglement.
Okay. Now, for example, for the practical applications, if for someone engineers such kind of devices, then how in a communication purpose, how we can propagate it, because you have an atom and these photon entanglement process.
Yeah, so what I mean, this atom-photon interactions are useful. I mean, they are currently not being used because of technical problems, but the hope is that one can, if we can have atom-photon interactions, then for sending information over large distances, we can use we can use photons. Because photons don't interact with the environment, so it is useful to send it over long distances. However, if we want to store information, then it's useful to use atoms. So if you want to store information for a significant period, and this significant period can be of the order of maybe milliseconds. So if I want to store information to the millisecond range, that can be then used for computation in an ion trap computer, for example. It is useful to have these atom photon entanglement. So I send information from one laboratory to another by using photons, but then use the atom photon interface to bring that information to a computational device.
Okay. Okay, thank you very much.
Thank you.
So now, next plenary talk from Professor Madan Singh, and let me introduce Professor Madan Singh. And he is a professor at National University of Lesotho, South Africa, in the Department of Physics and Electronics. He received his PhD in Material Science at GB Pant, University of Agriculture and Technology, Pantnagar, Uttarakhand, in 1998, India. Professor Singh's research interest includes material science, semiconductor, nanomaterials, theoretical and simulation research, condensed matter physics, etc. He is an active member of more than 10 international societies, organizations, committees, and editorial boards. And Professor Singh is a high-profile scholar who has published more than 50 articles in aggregate referred journals and author of 4 books. Now, I invite Professor Madan Singh, and you will be starting at 1. So 25 minutes for your talk and then 5 minutes for the discussions. Is there or not?
Sir, बात करिए उधर. Sir, let me check.
Okay.
I am calling.
Already joined, I thought.
No, he was joined.
But
I don't know why he is not audible.
Can you make a call to him?
We are calling.
Okay. The Professor Seth is there? Professor Seth is there?
Yes, I'm here.
Because the next speaker is not there, so I have one question again, if you don't mind.
Yes, tell me.
So completely you will be working, that is a completely qualitative analysis of this kind of the systems. For example, now as for the practical applications, you are saying that for the quantum computing application, it's be fine. But if we need a multiple entangled state in such system, is it possible to to create multiple entangled states using such kind of the impurities and these populations?
I think people have done experiments by using 2 atoms and 2 cavities. More than 2 cavities, I don't know people have whether they have done. I mean, theoretically, it is possible to consider many cavities, that is of course sure. But I don't know whether experimentally people have considered more than 2 cavities and 2 atoms and more than 2 atoms in different cavities. I don't know that. But multipartic entanglement is better to be prepared in ion traps, for example, or superconducting qubits.
Okay. Okay, in your slide number 30, there is a single and a double atom model, that's comparison, that you are saying that this alpha is a strength of the entanglement, right? You are saying that the strength.
Yes.
So how you are measuring that the strength of the entanglement? It is a tangle value you are saying that, or the?
Yeah. So if you have a pure state, then the local entropy. So you take you trace out one of the parties, you take the other party, and you find out the von Neumann entropy of that. You will see that it is a monotonically increasing function of that alpha.
Okay. Okay. Thank you. Thank you so much. Mr. Adarsh.
Sir, he is not picking phone.
Okay, so what?
Actually, he was here. He was present during the talk, but right now he is not picking phone. I don't know what's the problem. No, कोई नहीं है. So we should finish this session.
Should we close this session, or should we wait for a couple of minutes?
I don't know, because okay. So we should start the validity session.
Because, okay, I mean, no, it's up to you now. I hand over all the proceedings to you now. You do the rest of the process. Thank you.
Because Professor Veerpal Singh has some family problems and he is not able to join us. And I don't know why, what are the technical reasons that we are not able to connect with the Professor Madan Singh. So he was in the session and he was present, and why I don't know exactly. And right now he is not picking phone also. So to start the last session means validity session of this conference. And thank you, Nandan sir, for wonderful interaction with the Ujjwal Sen sir. And now we move forward. And I would like to invite Dr. Bhuvesh Joshi. He will tell us some experience how we managed, because only 2 or 3 minutes within that he will tell us how we managed this e-conference. So Dr. Bhuvesh Joshi, are you available?
Yes, yes. Thank you, Adarsh. Good afternoon to all of you. First of all, I thanks all of our respective speakers to give us some times in their busy schedule. I also thanks Mr. Adarsh and our organizing committee that give us some opportunities to make this on.
Now today everyone is going out of the range. I don't know what is happening. So sorry for all the technical problems we are facing right now. But since last 2 days, we are very frequent, and there were no technical glitches. In the last time we have some problems, but Now I would like to invite Dr. Mahipal Singh, the co-convener of this e-conference, and he is from Radhe Hari Government PG College, Kashipur, and I would like to invite him. Sir, please.
Thank you, others. Actually, this was a very good platform, virtual platform, through which we have interacted so many people's professors, scientists, and we received the blessings and wishes of so many experienced persons like Professor S.P. Chandolaji, Professor N. Nimai Singh, sir, and Durgesh Rai sir, S.D. Kaushik sir, Parmesh Singh, S.N. Pandey sir, and Pinaki Mukherjee sir, L.P. Provik sir, Prabhakar sir, Ujjwal Singh sir, and we have interacted so many magnetic personalities through this e-conference on this virtual platform. We have tried our best to organize this e-conference. You have seen that we have used some flavor in this conference, and nowadays there is a trend to conduct online conferences, webinars all over the world. We have also attended some webinars, but the publication of e-conference in the form of e-souvenir is a new idea. And the organizing secretary, Mr. Adarsh Kumar Chaudhary, is very dynamic and active personality. And he is actually my research student also. And I am feeling proud that I am having so active and energetic person with us. Dr. Bhuve Joshi ji, convener of this conference. Dr. Dr. Subhash Chandra Pokhriyal ji, who is the co-secretary of this organizing committee. And thanks to all the participants, resource persons. Now we will discuss the outcome of this conference. What is the outcome of this conference? And we will think over how this outcome can be used in the welfare of society. In the welfare of society. Thank you others, and all the participants and the resource persons. Thank you. Okay.
It is a matter of great pleasure that the chairperson of this conference, Professor Kamla Chanyal, ma'am, the principal, Government PG College, Bajpur, is also with us, and I welcome ma'am for being with us. And now I would like to invite Dr. Subhash Pokhriyal ji. He will present the summary of the conference which we get in last 2 days. Please, Pokhriyal sir. Pokhriyal sir, are you? Please unmute yourself, Pokhriyal sir. Unmute. कम यहाँ आ जाओ जल्दी से.
हाँ, now he's visible.
Actually, we got a message from Dr. Madan Singh. Actually, he cannot attend this webinar at this time because he is engaged in some meeting in South Africa in institution, and he's chairing the meeting. Sorry for he has sent sorry he could not attend this webinar, and sorry for inconvenience. Okay, thank you.
Good afternoon, everybody. So, advice to society. I started 2020. Professor S.C. Chandola, Head Department of Physics, Kumar University Nainital, was the patron of this e-conference. Professor Chandola inaugurated the e-conference and he talks about various aspects in physics. Professor Sachin Maheshwari, Technical University Delhi, was the chief guest of this conference. He told how physics may be more useful for the society. In session first, there were 5 presentations, including keynote address. The keynote address was given by Professor N. Nimai Singh, who delivered a very informative talk on neutrino oscillation and some unsolved issues. Dr. Durgesh Rai, Dr. S.D. Kaushik, Dr. Paramesh Singh, and Dr. Hemathinandan Pandey were plenary speakers of this session. All the speakers delivered their talks in a very nice way. The second session was started after lunch, in which 4 parallel sessions were conducted. For this session, we got several abstracts, out of which 44 were accepted for oral presentation. In these sessions, faculty members and research scholars present their research work. In day second, there were total 6 invited talks. Dr. Pinaki Mukherjee, Professor L.P. Prohit, Professor Prabhakar Singh, Professor Birpal Singh, Professor Ujjwal Sen presented their research work. Actually, it is very difficult for the government colleges to organize such a big event under difficult geographical and infrastructural conditions. For this purpose, the organizers of Government PG College Bajpur, Government PG College Ramnagar, and Government PG College Kachipur came together in a single platform in this pandemic situation. The e-mode of this e-conference is a new approach so that our faculty members, researchers, and young research scholars can take benefit of all the talks given by all participants. In this e-conference, total 450 participants registered. We hope various topics covered in this e-conference definitely very fruitful and motivated for all the young teachers and scholars. After the grand success of this e-conference, the organizers decided to organize such new more events. Thanks very much.
Thank you, sir. Thank you, Pokhriyal sir. And in the last time, this last session, now I would like to invite our principal, Dr. Kamla Chanyal ma'am, to share your views and give us blessings for that. Thank you, ma'am. And I should say vote of thanks also. Thank you, ma'am. मैम प्लीज अनम्यूट, आपकी आवाज नहीं आ रही है, आप उसको अपना माइक ऑन कर लीजिए. नहीं, मैडम प्लीज अनम्यूट योरसेल्फ. मैम आवाज नहीं आ रही है, आप अनम्यूट कर लीजिए अपने आप को. ये टच करेंगे, स्पीकर है वहां पर, स्पीकर को टच कर लीजिए. रेड कलर का बटन दिख रहा होगा. ये स्पीकर जब स्क्रीन को टच करेंगे तो वहां पर होगा, प्लीज.
हाँ
यस यस,
अब
नाउ इट इज ओके।
आई है?
हाँ बिल्कुल बिल्कुल आवाज आ रही
ओके
है। ओके
हाँ
ओके।
ओके, थैंक यू आदर्श। भौतिक विज्ञान की अंतर्राष्ट्रीय ई कॉन्फ्रेंस की मुख्य संरक्षक प्रोफेसर कुमकुम रौतेला, निदेशक उच्च शिक्षा उत्तराखंड, संरक्षक।
मैम फिर ज्वाइन हो गए, फिर आपने म्यूट कर दिया। अभी भी नहीं हुआ।
अब ठीक है?
जी 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 बिल्कुल।
अब ठीक है?
हाँ जी बिल्कुल ठीक है।
ओके ओके। भौतिक विज्ञान की अंतर्राष्ट्रीय ई कॉन्फ्रेंस के मुख्य संरक्षक प्रोफेसर कुमकुम रौतेला मैम, निदेशक उच्च शिक्षा उत्तराखंड, संरक्षक प्रोफेसर एस.सी. चंदोला, विभागाध्यक्ष भौतिक विज्ञान कुमाऊं विश्वविद्यालय नैनीताल, सभी आदरणीय वक्तागण एवं सभी सम्मानित प्रतिभागीगण, इस अंतर्राष्ट्रीय ई कॉन्फ्रेंस के समापन अवसर पर आप सभी के बीच उपस्थित होने पर मुझे अत्यंत हर्ष की अनुभूति हो रही है। आप सभी विद्वज्जन की भौतिकी प्रकृति विज्ञान की एक विशाल शाखा है। भौतिकी को परिभाषित करना कठिन है। कुछ विद्वानों के अनुसार यह ऊर्जा विषयक विज्ञान है और इसमें ऊर्जा के रूपांतरण तथा उसके द्रव्य संबंधों की विवेचना की जाती है। स्थान, काल, गति, द्रव्य, विद्युत, प्रकाश, ऊष्मा तथा ध्वनि इत्यादि अनेक विषय इसकी परिधि में आते हैं। यह विज्ञान का एक प्रमुख विभाग है। इसके सिद्धांत तो समूचे विज्ञान में मान्य है और विज्ञान के प्रत्येक अंग में लागू होते हैं। विज्ञान की अन्य शाखाएं या तो सीधे ही भौतिकी पर आधारित हैं या इनके तथ्यों को भौतिकी के मूल सिद्धांतों से संबंध करने का प्रयत्न किया जाता है। बहुत पहले इसको दर्शन शास्त्र
मैडम ये दोबारा म्यूट हो गया है।
प्रेरक है। स्पष्ट है कि इस तेजी से बदलते हुए विषय और इसके समाज तथा मानव जीवन पर पड़ने वाले प्रभावों की जानकारी सभी शोधार्थियों वैज्ञानिकों के लिए अत्यंत महत्वपूर्ण है। इसके दृष्टिगत इस कॉन्फ्रेंस का विषय समसामयिक एवं अत्यंत महत्वपूर्ण है। ज्ञान के प्रसार एवं नए विचारों के आदान प्रदान हेतु आयोजित इस 2 दिवसीय अंतर्राष्ट्रीय ई कॉन्फ्रेंस की सफलता का अनुमान इस बात से लगाया जा सकता है कि पिछले 2 दिनों में लगभग 450 प्रतिभागियों ने इस कॉन्फ्रेंस में भाग लिया। कॉन्फ्रेंस में लगभग 40 पेपर प्रस्तुत किए गए और 12 आमंत्रित वक्ताओं के व्याख्यान हुए। मैं बहुत कम समय में इतने सफल कार्यक्रम के कुशल आयोजन के लिए आयोजन समिति के संयोजक डॉक्टर भूपेश जोशी, सह संयोजक डॉक्टर महिपाल सिंह, आयोजन सचिव श्री आदर्श चौधरी और सह आयोजन सचिव डॉक्टर सुभाष पोखरियाल को बधाई देती हूं और आशा करती हूं कि इस प्रकार के कार्यक्रमों का आयोजन भविष्य में भी उनके द्वारा किया जाएगा। मैं माननीय उच्च शिक्षा मंत्री डॉक्टर धन सिंह रावत जी का आभार व्यक्त करती हूं। आपका आशीर्वाद हमें मिला। निदेशक उच्च शिक्षा उत्तराखंड प्रोफेसर कुमकुम रौतेला जी का उनके द्वारा दिए गए सहयोग एवं आशीर्वाद के लिए मैं आभार व्यक्त करती हूं। माननीय कुलपति कुमाऊं विश्वविद्यालय जी का भी मैं उनके आशीर्वाद के लिए आभार व्यक्त करती हूं। प्रोफेसर चंदोला जी का आभार एवं सभी प्रतिभागियों एवं प्रख्यात वक्ताओं का धन्यवाद करती हूं। मैं प्रोफेसर ओपी नेगी जी कुलपति उत्तराखंड मुक्त विश्वविद्यालय का इस कार्यक्रम से जुड़ने के लिए विशेष आभार व्यक्त करती हूं। अंत में आयोजन समिति के सभी सदस्यों को डॉक्टर भूपेश जोशी, डॉक्टर महिपाल सिंह जी, आदर्श जी और डॉक्टर सुभाष पोखरियाल जी को इस कार्यक्रम हेतु, सफल कार्यक्रम हेतु, बहुत अच्छा सफल कार्यक्रम आपका हुआ, इसके लिए बहुत बहुत बधाई आप सभी लोगों को। थैंक यू।
Thank you, ma'am. And on behalf of our organizing team, I would like to thank all the participants, means all my respected participants who participated in this conference, without which it was not possible for us. And also the participant who presented their oral presentation. I thank all of them. And also I would like to thank, in addition to means our chief guest in inaugural session, Professor Sachin Maheshwari, Dean Faculty of Technology, Delhi University. And I would like to thank all invited speakers, means Professor Nimai Singh sir, Professor Prabhakar Singh sir, Professor Ujjwal Sen sir, Professor L.P. Purohit sir, Dr. H.N. Pandey sir, Dr. Pinaki Mukherjee sir, Dr. Pramesh Singh sir, Dr. Durgesh Rai sir, Dr. S.D. Kaushik sir, who presented their views and enlightened us for the future working in physics and what is possible in physics in future. They gave us the knowledge. And I would like to thank all the chairpersons of different sessions. I would name them: Professor Y.K. Sharma sir from Government PG College Ranikhet, Dr. S.D. Kaushik from UGC CSR Bark Mumbai, Dr. Mukesh Pandey from Taiwan, Dr. Anil Singh NIT Rourkela, Dr. Nandan Bist Kumar University Nainital. And I want to give special thanks to our whole organizing team, our convener Dr. Bhuvesh Joshi from JIT Noida, co-convener Dr. Mahipal Singh sir from Government PG College Kashipur, Dr. Subhash Pokhriyal, Government PG College Ramnagar. And special thanks to Dr. Atul Upreti for this wonderful souvenir he presented for us, prepared for us. And I thank at last to our principal, Professor Kamla Chaniyal, for allowing us to try to organize this conference. And some information is also there. We will provide certificates for this e-conference within 10 days, because we will take some permissions from the Directorate of Higher Education, and after that we will provide through your mail, which you have registered through registration form or through feedback form. So please fill your feedback form in correct manner without any spelling mistake in whether it is name or in department. And I thank again to all of you for making this conference successful, and I hope we will meet again in the same platform. And I want to give a special thanks to Google Meet, who provided free of cost service to meet in a virtually. And so thank you, thanks a lot, thanks again. I hope we should, and especially to media who is covering all the news for this e-conference. So, and I missed the name, Dr. Sanjay Singhal from training session from Gujarat also. Thanks a lot. Bhuvesh sir, do you want to say?
Okay, others, all is complete?
Yes, sir. For my side, it is complete.
Okay, my phone is too hot. It's shut down at the event when I am talking. Now all things is okay. I thank you, all of you, all our speakers, all our participants. Thank you, all of you.
Okay, sir. Should I remove all of them?
You can close that, remove or close this event.
Thank you, organizing team.
If anyone
want to give some feedback to us? Do you have any opinion? Do you have some experience, or you want to share something?
It was a very bold step that you organized the international conference, and I highly appreciate this move. It was all fantastic, and I hope in future we will see more such conferences. I am Muhammad Abdul Ali Mansari, Assistant Professor, Physics, Government Degree College, Chudiala.
Thank you.
Thank
Okay,
you.
others, a couple of words I would like to share with you, with all of you. And first of all, I congratulate the whole organizing team and especially others and Bhuvesh, and such a fantastic conference you have organized in a very short time, and the kind of the speakers you have arranged in a very short time, and the number of the participants have registered, the way you have advertised the things, the way you approach the people of the university, of the the national level or the state itself. And I believe that the researchers definitely got the benefited from such a fantastic conference. They're having the very mesmerizing sessions. Unfortunately, yesterday I was out of the station. I had some important meeting, so I missed yesterday all the lectures. If it would be possible to have these lectures, you have recorded all lectures. If it is possible for sharing this one through the Google Drive or some other platform, I will be very happy to see them. And once again, I congratulate and I wish and near future and later or the sooner to be a part of this team, to be part of such a conference and to be participate in such a conference at a webinar, and where you do not require to move from one station to another station. Being in one single your office itself, you are at your home, one can participate and one can get all the information what exactly going in the present scenario or the recent trends in the physics is going on. Thank you very much, and finally I congratulate and keep it up, and thank you very much.
Okay, thank you, sir. But you already is a part of this organizing team.
I meant some other way of what I'm saying, that because I did not contribute much what you was expecting the way I am saying.
Okay, thank you, sir. And we will do something more. I hope so. Thank you, sir. And we will do something more. I hope so. Thanks a lot. So we should close that this event. Okay.
Others close
Please,
that
all
event.
of you remove.
If anyone,
please. Anyone? Do you have any question regarding certificate, etc.? Anyone want to say anything?
Any comment from the side of participants? Or suggestion?
Okay, thank you.